Well, hello, Jeff. It's wonderful to have you here with us at HICS 49.
Very pleased to be here. Thank you.
Wonderful. So what has been your most interesting part about HICS?
I think as the scientific program is just so incredibly diverse here. I'm not by nature a management systems or an information systems person, but it's wonderful to see such an interdisciplinary group and all the great work that's going on. And the environment here is not too bad either. I can stand it.
It tends to put people in a good mood for being helpful.
It does.
And so you're here as CTO of Emotiv,
That's
and
right.
It's been quite an honor for you to sit in on certain symposium with us and different workshops. And so you have two devices here on your lap as well. Could you explain the difference between these two claw-like sets? No.
Yes, okay. So this device is the Emotiv EPOC. This was our flagship product, and it's been on the market for several years. It's a 14-channel EEG device. We use salt water as an electrolyte with silver chloride pads, and then this whole device, all of the electronics sits in this little pod here, and we transmit the EEG data wirelessly after quite a bit of data cleaning up inside the headset. So this one has been used in about 60,000 different research labs around the world, and so it's pretty hard keeping up with what's going on in the entire field, but I try and keep across it.
Have you seen a more common use for the headset?
We originally envisioned it as a consumer device for gaming and for control, particularly by people who are maybe disabled, helping them to control their devices without hands. And we're seeing just a myriad of different things. So neuroscientists are buying it because it's inexpensive and gives pretty good data quality. It's not quite the same coverage as a 32 or 64 channel system, but the data quality from the 14 channels is pretty much comparable. And for a lot of neuroscience applications, people are only interested in the frontal lobes anyway, and we have very good coverage. We also measure temporal and parietal and occipital lobes with this device, and it's just finding an incredible number of uses. I've just been amazed. It's been used in music and art, architecture, systems research, and pure neuroscience as well. So, and we're getting quite a lot of interest in this particular device for the field of telemedicine as well, in remote, disadvantaged communities and in developing countries.
Well, there's interesting extensions even as information systems and sciences expand into health IT and we grow our area, that we might be able to make use of the headset in that realm.
Absolutely, yeah. Right now we haven't gone for an FDA approval, however, just because of the fairly onerous and costly nature of it, but my background is in medical product development and I know for sure this device will pass. We just don't really want to go through the paperwork and the QA systems at this point, mainly for the expense. It will add a little bit to the cost of the unit. So.
Yeah, and this is an interesting avenue, looking at doctors and their trust of data. And so we've seen a presentation here at HICS 49 around physicians trusting the data based on FDA approval versus it enhancing their interpersonal relationship.
Yeah.
So you mentioned FDA approval. Is it in fact something on the horizon?
Yes, definitely.
Okay.
Mm-hmm.
Great.
Yeah. So we have plans to go up in scale and also down in scale. So consumers, obviously, there are more of them, but they also stay at a lower price. In the medical community, there are less overall sales and more dollars per sale. So we have commercial imperatives in both directions to drive the system. This one is 14 channel. The typical clinical system would be 19. And what we're missing from this device, particularly for its original intent, we deliberately left out central line and motor strip sensors because it was designed as a BCI for able-bodied people who are walking around. So it was superfluous to have motor strip information there. If you're moving, it's the same as if you're imagining moving. So we didn't want to trigger anything unexpectedly. So the clinical direction that we'll be going will be at least a 19-channel system in the future. That may not be for a couple of years, and we'll be definitely going for an FDA approval for that device. In the downward direction towards consumers is more this device. So this one is Emotiv Insight, which is a 5-channel system. We still get coverage of frontal lobes, temporal lobes, so we have two lateral sensors here, and we have one that's actually on the center line of the parietal region, so just the junction between parietal and occipital. So we can see a lot that's going on in the back of the head with this system.
Have you seen any P300 detection from
this device? It's a little soon for people to be doing P300, but I've actually tested it in-house with P300 paradigm systems, and it does work.
Okay.
Yeah.
That's exciting. And so to clarify for our audience, P300 being this aha response that you might have to an odd paradigm appearing,
Yes.
and you described the popular Donchian speller that is a matrix that allows you to be able to tell the words or spell out the letters that you want without someone having to prompt you, so you can tell us.
That's right. Yep. And that's particularly useful for people who are locked in, have no muscle control whatsoever. One of the beauties of EEG is that you also pick up muscle signals if they're there. And it's not regarded as a beauty in the EEG business, it's actually regarded as an artifact or a noise. We developed a system to extract the information from the artifacts, and we can detect operation of specific muscle groups in the facial region particularly, so we can tell whether you're clenching your teeth, smiling, blinking, winking, and we can actually use those things as additional triggers in our BCI systems. So if somebody still has the ability to blink, they can use the blink reflex, which is a much more immediate detection. It's actually much simpler to extract from EEG than a brain signal.
Certainly. And there was an audience member that brought up, of course, the famous Stephen Hawking and
Yes.
our concerns for losing such great minds to becoming further locked into their bodies. And you aptly said, well, he still has the muscle control, which in this case is still a lot more, it's a quicker signal than a brain-computer interface purely would provide us.
Yeah.
So would this perhaps afford us a hybrid system?
Yes. Yeah, we expect so. We would probably go for a higher channel count system so that he got used to using brain signals as well as the muscle signals, and so if, God forbid, the muscle control ever disappeared, he would still be familiar enough with the system to not lose too much momentum in what he's doing, because we really want everything that could come out of Stephen Hawking's brain.
Yes. Now, would you see that being a longer time of training that he would need?
Generally, once the system is trained, it's pretty accurate to reproduce. I have training signatures that are 5 years old that I can still reactivate, and generally there's only maybe 2 hours of training in total on those systems. In fact, you can get quite a good response from even 20 or 30 seconds of training once you become experienced in how to do it. So.
Now, is that built into the system itself as far
Yes.
as an algorithm that's learning?
Yeah, so we have 2 or 3 different types of algorithms in the system. So we have specific algorithms to detect muscle group activations and to classify those. And that's generally fairly universal across people. Everybody's face is more or less the same. We have a little bit of customization built into that because everybody's face isn't exactly the same. And so you can adjust individual sensitivities to get detections working better. And then we have a training system behind that kind of detection as well. So you can, if, for example, you're partially paralyzed, you may not have the same sort of muscle responses, but you're still trying to smile. Well, we can actually train the system to recognize that and substitute that into the facial recognition algorithms. We have universal algorithms for measuring emotional detections. So we can measure classical valence and arousal. So we measure approach and negativity just by effectively bilateral lateral activations.
In the brain.
In the brain, yes, by lateral asymmetry. Yes, thank you for pointing that out.
Well, just to clarify, since we
Yeah.
transitioned from things that we can detect from the face, which you have a
Yeah.
lot of that built into the system as well.
That's right, yes. So we then go into the brain signals, and so we use various different algorithms which were trained on large groups of volunteers to elicit specific emotions or responses, and we use machine learning to generate global algorithms that everybody responds in particular ways. So happy or sad, excited or calm. We have detections that can feedback when you're meditating properly. We have stress detections, or stress or frustration. That was a fun one to actually run the experiments for, deliberately frustrating people.
Well, this is really particularly important. In dealing with individuals who are living locked in, not being able to tell us outright when they're feeling frustrated or when they're having these stressful moments, especially in working with the technology. So being able to have a system that's able to also highlight that to the researcher, to the caregiver, is really key.
That's exactly right. So that in future our algorithms will actually work to close the loop there. So if your mental commands aren't working properly, we can detect that you're getting frustrated, and we'll actually start to do something about it.
That's great. And so this is a really exciting part about the work and how we're able to outreach to truly help individuals and improve quality of life. And we've talked a bit about people who are locked in, but also individuals who are elderly or in other capacities that they might not be able to articulate what they're feeling, but they're still feeling and thinking that way.
Yes, absolutely. In fact, an interesting study that we're doing with the University of Edinburgh is on the influence of architectural spaces on elderly people. And so they're kitting out a whole group of elderly people and letting them walk in the park and finding out what parts of the park are attractive and which are repulsive. And finding reasons why people should get out into nature and what's going to encourage them to do that. And they're designing the spaces to encourage people to get out and walk around, which is great for older people who otherwise sit in a chair and watch television or possibly play on the internet if they're commercially savvy.
Well, and interesting to the people designing the spaces.
Yes,
as well.
absolutely, yes. So that's the purpose really, is to encourage people to use them. And so that's an interesting study that we can do.
That's neat. And thinking about how it translates into the system space as well, where we're very much concerned about good design and how we're able to improve design for our users. So being able to have a marker that shows what someone is feeling in their frustrations or their enjoyment at certain points in time.
Yes, so we can measure those kind of responses, and that helps in the design process. In fact, in the initial inquiries that we got in the gaming industry were for helping to design the games rather than helping to play the games.
Okay.
And so that situation applies across the board to designing any system. We also have the capability, obviously, to measure cognitive load, distraction rates, and many other things that are relevant to designing systems.
I think all very relevant to our community.
Absolutely.
So is there anything you would perhaps want to tease us about that's on the horizon for
Yes, so I think the excitement for us at the moment is that we're now starting to, particularly with this device, but also with the new generation of this model, both of those products now talk to mobile devices using a low energy Bluetooth protocol. So you can walk around with your phone and monitor your responses to the world, and you can stream that data in real time or later. And we're gathering basically a large database of normal population, which consists of very normal and very abnormal individuals, of course, and people who are going through particular issues, maybe brain trauma or some other things, and we can look at longitudinal data. So we're gathering from that information a lot of data about how people look in the general community. EEG traditionally has been either used in a research context for studying specific situations, or for the medical use, which is essentially if you have a suspected stroke or a suspected case of epilepsy or autism, you may well get a brain scan, but otherwise there's no reference point, there's no data whatsoever. We're very excited to start progressing on building a massive database of people. It's essentially going to be a normative database, but we'll also build information about what happens to people over time. For example, if we know that they're studying a language, we can look at the cognitive load during the early phases and how that progresses as they master the language. Same with learning a musical instrument or a new piece to play.
Sure, or within the classroom.
Having a meeting. There's already some great work I've seen in this conference about dynamics of meetings. Mm-hmm. So that kind of information is going to be very valuable long term, and specifically in the longitudinal case, we'll be able to use big data analytics to start looking for biomarkers for specific events. So maybe as people age and start to get forgetful, are they going to progress into Alzheimer's or not?